Now, problem number 47, I believe, in the section 12.4, I believe. The proof that I saw is good, but it's a little more rigorous if you bring it down to what happens in one specific small region and then build that up by partitioning. So we say, and this is almost identical to what was said on the paper that I reviewed, but I'm going to do it in terms of small area increment. So consider small area increment delta A in the XY plane in a sample point X star, Y star within the region. Then at the point X star, Y star, Z star being the Z value that's implicitly defined by the function f of x, y, z, corresponding to X star and Y star, is the gradient of f at that point, f being the level surface. Okay, we're familiar with the fact that the gradient of a level surface is normal to the surface. Okay, then if we project del f onto the vertical direction, or project del f onto the k vector, divide that by the magnitude of del f, we get the cosine of gamma, where gamma is this angle here between the normal to the surface and the vertical direction. And that is the same angle, and I'm waving my hands a little bit, but it's the same angle to which the area delta A needs to be tilted to give you the corresponding area of delta S. The angle by which delta S is tilted with respect to delta A. And then it's a very simple trigonometric argument that the ratio of delta A to delta S is the cosine of gamma. So that delta S is delta A over the cosine of gamma, which is magnitude of the gradient divided by the magnitude of the projection times delta A. And then you simply partition the region and so forth, form a partition so that you partition the region into a bunch of small increments, each with a sample point X star, Y star, so that this argument applies to every one of them. And you find that your surface area is the integral over the region with respect to area of this expression. Kept putting arrows over the F's and then smudging them out, so that's the reason for all the smudges. And then sometimes I miss the arrow over the del. Okay, probably other places too. In any case, then that's equal to this integral, and that's what was to be proved. And the whole idea of confining attention to one small increment where the deviation of the surface area, the difference, the ratio of the surface area, actual surface area to the surface area of a plane region orthogonal or perpendicular to the gradient is now what the rest of my sentence say. The ratio of the area of the actual region to the plane region that you're approximating by this assumption approaches 1 in the limit as the size of your, let's say, the mesh of your partition, okay, the maximum size of an element of your partition approaches 0, maximum diameter of the region or whatever. Many ways to say it. Okay, so, and there's still a limiting argument that needs to be made. And this is the one thing I kind of want you to be aware of, that there's a little bit of stuff here that hasn't been done with complete rigor, but this is the framework in which you need to achieve complete rigor in this argument.